course despite streaming visible gas. If 3I Atlas is natural, we can explain none of this. If it isn't, we may have just witnessed our first interstellar visitor under intelligent control. So, what is hiding behind these impossible signals? Radio telescopes have spent generations sweeping the sky for a single artificial pulse. A beacon, a whisper, some coded invitation from another world. But in the silence, another channel has opened. Every so often, a solid body crosses the gulf between stars and enters our solar system. A macroscopic technosignature, if any exist, would look like this. Not a signal, but an object. Since the dawn of modern astronomy, only 3 such visitors have ever been confirmed. The odds are staggering. For every 100 billion comets that circle the Sun, only 1 or 2 have come from another star. Each arrival is a cosmic lottery ticket, a chance to catch something built, not born. Traditional SETI, with its focus on radio and laser signals, assumes that civilizations broadcast. But what if the best evidence is physical, silent, inert, drifting through space? Objects can preserve information, technology, even intent long after their makers are gone. Unlike a fleeting transmission, a macroscopic artifact endures. It can be studied, measured, and if the timing is right, intercepted. The scarcity of these interstellar objects makes every detection a global event. Oumuamua in 2017, Borisov in 2019, now 3I Atlas. Each one is a singular opportunity, a probe from a time and place we may never see again. Their rarity means that even a single anomaly carries weight. The universe offers few second chances. SETI's original vision was shaped by the tools of its era: radio dishes, signal processing, a search for patterns in the noise. But the discovery of Oumuamua rewrote the playbook. Suddenly, the search for technosignatures included not just what we hear, but what passes by. 3I Atlas is not just another comet. It is evidence in transit, a messenger from another system, and perhaps, if we're prepared to look closely enough, a sign that we are not alone. On May 7, 2025, the Transiting Exoplanet Survey satellite, TESS, recorded a faint fast-moving object against the thick star fields near the galactic center. At the time, no alert went out. The signal was buried in a digital sea of stellar clutter, its motion too subtle for automated triggers, its glow lost among thousands of background stars. For nearly a month, the object swept onward, captured night after night in TESS full-frame images. Each exposure stacked another faint trace onto archival hard drives. It wasn't until July 1 that the Atlas survey, scanning from its Chilean node at Riordo, flagged an anomaly. The object had brightened sharply, fivefold since TESS first caught it. Yet its position still hugged the crowded bulge of the Milky Way, a region notorious for hiding transients in plain sight. The Minor Planet Center logged the alert, and within 24 hours the world's observatories pivoted to follow up. In the days that followed, teams combed through old data. The Zwicky Transient Facility and Pan-STARRS both turned up pre-discovery images from late June. Their own records showed the object's trail as it moved steadily across the sky. Amateurs joined the hunt, sifting through public archives, their finds filling in gaps from June 14 through the end of the month. Each new point on the timeline added detail to the light curve, revealing a surge in brightness that outpaced any simple geometric explanation. The culprit was the sky itself. The object's approach from the direction of Sagittarius meant that even the most sensitive surveys struggled to separate its signal from the background. Only after the July announcement did the full scope of its early activity become clear, thanks to a forensic sweep through terabytes of archival data. For the TESS and Atlas teams, the discovery was less a single spark than a slow burn, lit weeks before anyone realized an interstellar visitor had arrived. Between May 7 and June 3, 3I Atlas brightened by a factor of 5, an increase that defies the usual playbook for distant comets. Standard geometry predicts only a modest rise, maybe 1.5 times brighter, as the object shifts from 6.36 to 5.46 astronomical units from the Sun. Instead, photometry from TESS, ZTF, and Atlas shows a surge fivefold, steady, and persistent across nearly 0.9 astronomical units of travel. Each survey's numbers line up cross-checked against field stars and synthetic solar analogues with systematics below 1/10 of a magnitude. This isn't a brief outburst or a fluke of instrumentation. The light curve reconstructed from nightly stacks and shift-tracked exposures draws a clear arc rising smoothly, even as the object threads through the crowded galactic bulge. At 6.36 astronomical units, activity is not expected. Water ice stays frozen. The sun's warmth is a distant memory. Yet the coma is already visible, and dust cross-section measurements jump from about 300 square kilometers in May to over 1,700 by July. The numbers hold up under scrutiny, with error bars tight enough to rule out random scatter or background confusion as the cause. Stacking up the flux, the odds tilt sharply away from geometry alone. The excess light demands an explanation, one that fits both the timing and the scale. No single survey, no matter how deep, can account for the magnitude of the change. The data laid bare leave little room for ambiguity. 3I Atlas was already active and already an outlier before it ever made the official record. The search for answers begins with the numbers. A five-fold jump in brightness, outpacing every geometric prediction, demands more than a passing glance at the data. Astronomers run through the usual suspects: instrumental error, background confusion, a lucky line of sight through the galactic bulge. Each is tested, cross-checked, and ultimately found wanting. The light curve holds steady across telescopes and continents, its arc too smooth for a fluke and too early for classic cometary activity. Some suggest the object's true closing speed might have been underestimated, masked by the dense stellar fields of Sagittarius. But even after correcting for crowding and recalibrating the photometry, the excess flux remains. The numbers simply don't add up to a natural slow burn. That leaves the door open to bolder ideas. Could 3I Atlas have fired thrusters and engineered braking maneuver to match solar system velocities? It's a hypothesis that lives on the fringe, but the timing fits the data. A controlled deceleration executed far from the sun would explain the early persistent brightening without relying on water, ice, or familiar volatiles. If so, the object's activity would be the signature of intent, not accident. Yet for every speculative leap, a counterweight of caution. The sky is notorious for tricking even the most careful observers, and the burden of proof is heavy. As the debate turns, attention shifts to the chemistry of the coma, where the next clue may be hiding in plain sight. VL spectrographs tuned to the faintest whispers of atomic light picked up a puzzle in the coma of 3I Atlas. Nickel lines, clean and well-resolved, rose above the background. Yet iron, which should have been there in lockstep, was nowhere to be found. The team at Paranal spent nights double-checking calibration